Electricity and magnetism were regarded as two distinct topics in physics. In 1820, the Danish scientist Hans Christian Ørsted discovered that a compass needle is deflected when an electric current flows nearby. At that point, the attraction or repulsion between two magnets was a well-established fact. What Ørsted discovered is that the effect of a current-carrying conductor on a magnetic compass is similar to the one of a permanent magnet. We can conclude that any conductor through which an electric current has been established creates a magnetic field in the surrounding area. We call this the magnetic effect of an electric current. There are many practical applications of this discovery. Electric motors are one example. We can increase the strength of the interaction between the circuit and the magnetic compass by using a coil or a solenoid instead of a straight wire. It is also worth mentioning that the strength of the magnetic field produced by a coil or a solenoid can be significantly increased when an iron core is added. This setup is often referred to as an electromagnet. The strength of the magnetic field produced by an electromagnet depends on the magnitude of the electric current flowing through it. The higher the current, the stronger the field. The direction of the magnetic field created by an electromagnet can be easily changed by simply changing the direction of the current that flows through the coil. Ørsted's discovery shows that electricity can be used to create magnetism. The next logical step is to investigate whether magnetism can be used to produce electricity. There are a couple of obvious ways of trying to produce electricity using a magnetic field. First, we can place a strong magnet into a coil and try to see if an electric current is generated in the circuit of the coil. The ammeter does not show any current. The second obvious attempt would be to set up two electric circuits, run a current through one of them, and hope that the current appears in the second one. To ensure that the two circuits are as close as possible to each other, I'm going to put the electromagnet inside the large solenoid. The ammeter does not show any current. So time to pack up, go home, and try another day. But wait, the ammeter indicates a current when the electromagnet is switched off. Even more, the ammeter also indicates a current when the electromagnet is switched on. The only difference is that the current flows now in an opposite direction. Let's now go back to our first setup. The ammeter indicates the presence of an induced current when the magnet is removed from the coil. Furthermore, a current is also induced when the magnet is brought back inside the coil. The only difference, again, is the direction of the current. The two experiments demonstrate that magnetic fields could produce electric currents. This is called electromagnetic induction. The phenomenon of electromagnetic induction was discovered by the English scientist Michael Faraday in 1831. His key insight was to notice that a changing magnetic field can induce an electric current into a coil. Let's get back to the two experiments. In the first one, the strength of the magnetic field at the location of the coil decreases as the magnet is moved away and increases as the magnet is moved back into the coil. There is no induced current when the magnet is resting inside or outside the coil. In the second experiment, when the electromagnet is switched on or off, the current through it changes briefly, from 0 to a steady value when switched on, and from that value back to zero when it is switched off. Consequently, the magnetic field of the electromagnet is changing. When a steady current flows through the electromagnet, its magnetic field remains constant.